Open your phone. Point your camera at a dog. In under a second, your phone knows it's a dog, not a cat, not a table, a dog. It can tell you the breed. It can find its eyes. Now here's the question nobody stops to ask. How? Your phone doesn't have eyes. It doesn't have a brain. All it has is a grid of numbers, raw pixel values, and a single mathematical operation that transforms those numbers into meaning. That operation is called convolution. It's the foundation of every convolutional neural network, and it's the reason machines can see. Today, we're going to break apart the math. No code, no libraries, just the raw equations and the intuition behind them. So, what is an image to a computer? It's a matrix. A 1080p photo is a grid, 1920 columns, 1080 rows, and 3 channels for red, green, and blue. Each cell holds a number from 0 to 255. No shapes, no edges, no meaning. Just numbers. The problem, how do you extract structure from a flat wall of numbers? The answer is convolution. You take a tiny matrix called a kernel, typically 3 by 3, just 9 values. You place it on the top left corner of the image. Then you do something beautifully simple. Multiply each kernel value by the pixel underneath it and add up all 9 products into a single number. Formally, for a 2D image and a kernel, the output at any given position is the sum of the element-wise products of the kernel and the local image patch. 9 multiplications. 1 sum, 1 number. That number tells you, how strongly does this local patch match the pattern encoded in my kernel? Now slide the kernel 1 pixel to the right, do it again, get another number. Keep sliding across every row, down every column, and you build an entirely new matrix called a feature map. It's a heat map of where in the image a specific pattern was detected. And here's the part that should give you chills. The pattern the kernel detects is entirely determined by its values. Imagine a kernel where the top row is all negative ones, the middle row is all zeros, and the bottom row is all ones. That kernel responds strongly wherever there's a sharp vertical brightness transition, dark on top, bright on the bottom. That's a horizontal edge. Rotate those values 90 degrees and you detect vertical edges. Change the numbers and you detect corners, curves, blobs, textures, any local pattern you want. But here's the real insight. In a CNN, you don't hand design these kernels. The network starts with random values and learns the optimal ones through training. It discovers what patterns matter for the task entirely on its own. Nobody tells the network what an edge is. It reinvents the concept from raw data, because the math demands it. Now let's talk about what happens to the shape of your data as it moves through convolution. This is where most people get confused, and where the real engineering intuition lives. 3 hyperparameters control everything: kernel size f, stride s, and padding p. And they're all connected by one master formula. O equals the floor of the quantity w minus f plus 2p divided by s plus 1. W is the input width, O is the output width. This single equation governs the spatial dimensions at every layer of the network. Let me walk you through 3 cases to build your intuition. Case 1, no padding, stride 1. You have a 28 by 28 image. Like a handwritten digit, apply a 3 by 3 kernel. O equals the floor of 28 minus 3 plus 0 divided by 1 plus 1, which equals 26. Output, 26 by 26. You lost a 1 pixel border on every side. This is the border effect. The kernel can't center on edge pixels without hanging off the image. Stack 10 layers without padding and your 28 by 28 image shrinks to 8 by 8. 30% of your spatial information erased. And the borders, where critical features might live, get systematically underweighted. Case 2, same padding. Now add a 1 pixel border of zeros around the input. Padding p equals 1, O equals the floor of 28 minus 3 plus 2 divided by 1 plus 1, which equals 28. Output equals input. The zeros don't add real information, but they let the kernel visit every pixel, including corners and edges, with equal importance. This is called same padding, and it's the default choice in most modern architectures. Case 3, stride 2, downsampling. Keep padding at 1, but now the kernel jumps 2 pixels between applications. O equals the floor of 28, minus 3 plus 2 divided by 2 plus 1, which equals 14. Resolution halved in a single layer. This is how CNNs progressively compress spatial information as you go deeper. Early layers see fine-grained details at full resolution. Deeper layers see abstract patterns at lower resolution. It's a deliberate architectural trade-off. You sacrifice where to gain what. Now here's why convolution isn't just elegant. It's efficient in a way that borders on miraculous, and it comes down to 2 principles. Consider the alternative. A standard fully connected layer on a 28 by 28 by 3 color image with 64 output neurons requires 28 times 28 times 3 times 64, which equals 150,528 parameters. Every pixel connects to every neuron. Massive, wasteful. A convolutional layer doing the same job, 64 kernels, each 3 by 3 across 3 channels needs. 64 times the quantity, 3 times 3 times 3, plus 1, which equals 1,792 parameters. That's an 84 times reduction, and the output is richer. 64 full spatial feature maps, not 64 scalar values. Two ideas make this possible: weight sharing. The same 3x3 kernel is reused at every spatial position. You're not learning separate detectors for the top left corner and the bottom right corner. You're learning one pattern detector that works everywhere. This encodes a powerful assumption about images. If a feature is useful to detect in one place, it's useful to detect everywhere. An edge is an edge no matter where it appears. Local connectivity: each output value connects only to the small f by f patch underneath the kernel, not to the entire image. This reflects a fundamental truth about visual data. Nearby pixels are more related than distant pixels. Convolution bakes this spatial prior directly into the math. A pixel in the top left doesn't need to know what's happening in the bottom right to understand its local neighborhood. Together, weight sharing and local connectivity are why CNNs can process images with millions of pixels without exploding in size. A fully connected layer on a 1024 by 1024 RGB image would need over 3 billion parameters in just the first layer. A convolutional layer, a few thousand. Same expressive power, a fraction of the cost. And this brings us to the final idea, the one that makes it all click. When you stack convolution layers, something extraordinary emerges. The first layer's kernels learn to detect simple things: edges, gradients, color boundaries. But the second layer's kernels don't operate on the raw image anymore. They operate on the first layer's feature maps. So they learn to detect combinations of edges, corners, curves, T-junctions. The third layer detects combinations of those combinations: textures, eyes, wheels. By the fifth or sixth layer, the network recognizes entire objects, faces, cars, tumors. Each layer performs the exact same operation, the sum of products between the input and the kernel, but because each layer's input is the previous layer's output, the abstraction compounds. Simple local patterns compose into complex global understanding. Edge plus edge becomes corner. Corner plus corner becomes eye. Eye plus nose becomes face. This is how self-driving cars see lane markings, how medical AI spots tumors invisible to the human eye, how your phone separates your face from the background in portrait mode. It's all the same equation. One small kernel, sliding across a grid of numbers, learning to see. If this clicked for you, hit like and subscribe. Next time, we're going inside the attention mechanism, the math that lets transformers look at everything at once instead of one patch at a time. See you then.